electrical energy is generated in a zinc-copper voltaic cell. In a zinc-copper voltaic cell, a simple single replacement reaction is compartmentalized. During the process, zinc metal will undergo oxidation by losing 2 electrons, and aqueous copper 2 plus cation undergoes reduction by simultaneously gaining 2 electrons. The net ionic equation for the process is written as follows, where solid zinc metal with an oxidation state of 0 reacts with aqueous copper 2 plus cation to form aqueous zinc 2 plus cation and copper metal. The chemical reaction for the process may be written as follows, where solid zinc metal reacts with aqueous copper 2 nitrate to produce aqueous zinc nitrate and copper metal. The generation of energy in a voltaic cell will be easier to understand if the chemical equation is rewritten first as an ionic equation and then a net ionic equation. The ionic equation for the process is written as follows, where a solid zinc metal reacts with aqueous copper 2 plus cation and 2 moles of aqueous nitrate anion to produce aqueous zinc 2 plus cation, 2 moles of nitrate anion, and copper metal. The net ionic equation is written by excluding the spectator ion, where the spectator ion is that ion whose oxidation state remains unchanged during the entire reaction. In this case, the oxidation state of the aqueous nitrate anion begins at -1 and ends at -1. Therefore, the oxidation state of the nitrate anion remained unchanged, and that ion represents the spectator ion. The net ionic equation only shows those species who participate in the chemical reaction, where zinc metal reacts with aqueous copper 2 plus cation to produce aqueous zinc 2 plus cation and copper metal. From the net ionic equation, half reactions may now be written. The oxidation half reaction involves the zinc metal, where zinc metal undergoes oxidation to form aqueous zinc 2 plus cation and 2 electrons. The reduction half reaction involves the aqueous copper 2 plus cation. Aqueous copper 2 plus cation will accept 2 electrons through the process of reduction to produce solid copper metal. The values for the standard reduction potentials for each process are derived from a table of standard reduction potentials. The standard reduction potential for aqueous copper 2 plus cation is positive 0.34 volts. The standard reduction potential for aqueous zinc 2 plus cation is negative 0.76 volts. During this reaction, aqueous zinc 2 plus cation does not undergo reduction. However, solid zinc metal undergoes oxidation. To determine the oxidation potential, simply reverse the sign of the reduction potential for the aqueous cation. Therefore, the oxidation potential for the solid zinc metal is actually positive 0.76 volts. The total amount of electrical energy generated for this particular reaction is determined by adding the reduction potential for aqueous copper 2 plus cation, which is positive 0.34 volts, to the oxidation potential for solid zinc metal, which is positive 0.76 volts. Therefore, the reading on the voltmeter, and in fact the overall cell potential, or E cell, for this reaction will be 1.10 volts. In the voltaic cell, the two half reactions are allowed to occur in two different half cells. In one half cell, zinc metal will undergo oxidation, releasing two electrons, which will travel by wire to the half cell containing the copper 2 plus cation. The copper 2 plus cation will then undergo reduction. Because the zinc metal provides electrons for the reduction process, the zinc metal is called a reducing agent. Because the copper 2 plus cation will accept the electrons released by the oxidation of zinc metal, the copper 2 plus cation represents the oxidizing agent. The reading on the voltmeter, based on the two half reactions under standard conditions, will be 1.10 volts. This animation illustrates the overall processes that occur in a zinc-copper voltaic cell, where in one half cell, zinc metal undergoes oxidation, releasing two electrons that will travel by wire through a voltmeter, generating a voltage of 1.10 volts, to the other half cell, which contains a copper electrode, where the reduction of aqueous copper 2 plus cation occurs. Notice that during the process, the reduced copper 2 plus cation forms copper metal, which plates onto the copper electrode. And because the zinc electrode is undergoing oxidation, the zinc electrode is essentially dissolving. The circuit is closed by use of a salt bridge, which contains an aqueous salt. This concludes my explanation of how electrical energy is generated in a zinc-copper voltaic cell. Hopefully this video has been helpful. Thanks for watching.